Crater Lake has a reputation built on clarity, depth, and stillness. That is precisely why one question keeps returning with unusual force. Could a lake formed by explosive volcanism, sitting inside an active caldera, ever behave like Lake Nyos in Cameroon and release a deadly gas cloud? Could a body of water this deep, this isolated, and this geologically restless hide a hazard that remains invisible until the moment it matters? And if the lake floor is still fed by hydrothermal systems, how much reassurance is there in the fact that the surface looks calm and blue from the rim? USGS describes Crater Lake as a caldera lake formed by the collapse of Mount Mazama about 7,700 years ago, with a maximum depth of 594 meters, 1,949 feet, while NPS and USGS both confirm that the volcano is still considered active. The comparison to Lake Nyos is not casual. Lake Nyos was a very different kind of lake, with a very different internal chemistry. But the event that made it infamous was also a reminder that water can conceal gas for a long time before suddenly releasing it. USGS reports on Lake Nyos show that dissolved carbon dioxide built up in the bottom waters, supported by a volcanic source beneath the lake, and that the sudden release in 1986 produced a lethal cloud that moved into surrounding low-lying areas. The same USGS material also notes that Lake Nyos and the nearby Lake Nyos were examples of dangerous gas-rich crater lakes with stagnant bottom waters. Crater Lake, though, does not match that profile. According to USGS and National Park Service sources, the lake overturns seasonally, mixes with the atmosphere, and does not allow dissolved carbon dioxide to accumulate in the same way. A USGS open file report on the Crater Lake region states that the upper 200 meters of the lake overturns and equilibrates with atmospheric gases twice a year, and that any excess dissolved carbon dioxide comes out of solution without building up to lethal concentration. The same report adds that water between 200 meters and the bottom mixes with the upper lake over roughly 2.5 to 3.5 years. That does not mean the lake is geologically quiet in the ordinary sense. It means the hazard profile is different. Crater Lake still receives heat and salts from hydrothermal vents on its floor, and USGS has documented that the lake bottom contains hydrothermal inputs that affect its chemistry and ecology. In a broader USGS account of the lake, the agency notes that research with submersibles and sonar discovered thermal vents, and that more recent monitoring shows future volcanic activity is likely to remain concentrated in the western half of the caldera. The same USGS page says the volcano is expected to erupt again at some point, most likely beneath the water's surface, and that water interacting with magma could produce hydrothermal eruptions. The key distinction is that hydrothermal activity is not the same thing as a limnic gas bomb. Lake Nyos was dangerous because deep water trapped a large volume of carbon dioxide until the system destabilized. Crater Lake, by contrast, has a large, cold, well-mixed water column, a strong seasonal exchange with the surface, and a long record of dilute chemistry rather than concentrated gas loading. Older National Park Service material describes Crater Lake as a low-activity volcanic lake with active hydrothermal springs on the bottom, but minimal flow rates and minerals greatly diluted by more than 4 trillion gallons of water. That source also says the slow turnover at Crater Lake appears rapid enough to prevent a buildup of dissolved carbon dioxide at depth. The scale of the lake matters here. Crater Lake contains about 5 trillion gallons, 19 trillion liters, of water and covers roughly 21 square miles, 54 square kilometers. It is deep enough that the lower layers remain cold and stable, but it is also exposed to wind mixing and winter convection that helps circulate water through the upper part of the lake. USGS studies have described the lake as thermally stratified in late summer and fall, but mixed in winter and spring by wind energy and cooling, with the epilimnion generally only 5 to 20 meters thick during stratification. That is not the behavior of a stagnant basin quietly storing gas in the dark. There is another detail that often gets lost when the Lake Nyos comparison is repeated. Crater Lake does not have the same kind of direct gas conduit and trapped deep water reservoir that made Nyos dangerous. In the Lake Nyos case, USGS reports point to deep magmatic carbon dioxide gradually migrating upward into the lake and accumulating in the bottom waters. At Crater Lake, however, the best documented geochemical studies show a different pattern. The lake is well mixed. The water chemistry is relatively dilute, and any carbon dioxide entering the system is handled by turnover and equilibration, rather than being held in a stagnant bottom layer. USGS publications also report that chemical and isotopic analyses found Crater Lake to be well mixed, and that the upper part of the lake exchanges gases with the atmosphere on a recurring basis. Still, the lake is not being described here as a harmless pond. It sits inside Mount Mazama, a volcano that USGS says is active, with a complex history of overlapping shield and stratovolcanic growth, a catastrophic collapse, and later eruptions within the caldera. The final climactic eruption created the modern basin, and later activity formed Wizard Island and other volcanic features inside the lake. USGS states that more recent monitoring suggests future activity will likely occur in the western half of the caldera, and that there is even the possibility of a new vent on the flanks of Mount Mazama or nearby. That makes Crater Lake a place where the main concern is not a sudden limnic suffocation event, but rather volcanic unrest, underwater eruption, hydrothermal explosions, and seismic changes that could alter the lake's behavior. The shape of the hazard is subtle enough that it can be misread from the rim. A still blue surface can suggest dormancy. A deep basin can suggest permanence. But Crater Lake is fed from above by precipitation and snowmelt, loses water through seepage, and remains connected to a hot subterranean system beneath the caldera floor. NPS notes that the lake's water level is maintained by precipitation, evaporation, and seepage through porous rocks, and that the volcano beneath it is expected to erupt in the future, most likely under the water. These are not the ingredients of a Lake Nyos repeat, but they are the ingredients of a lake whose chemistry and physics are shaped by a living volcanic system. That distinction is why the real question is not whether Crater Lake can suddenly become Lake Nyos. The more serious question is what kind of volcanic lake it is, and what kind of danger would come first if the system changed. USGS and NPS sources point toward a lake that is too large, too mixed, and too diluted for Nyos-style carbon dioxide accumulation, yet still close enough to magmatic heat that hydrothermal changes matter. Crater Lake is unusual because it combines extreme depth, clear water, and hidden geothermal activity. That combination makes it scientifically important and volcanically active, but not on the evidence available, a known carbon dioxide trap waiting for a catastrophic release. The uncertainty is not whether the lake is connected to volcanic heat, it plainly is. The uncertainty is how that heat might express itself next, and whether any future change would come as gas, heat, fault movement, or a submerged eruption beneath the basin floor. The reason Crater Lake continues to attract this kind of attention is that it sits at the intersection of two very different scientific problems. One is the behavior of a deep volcanic lake that interacts with hydrothermal fluids, seasonal turnover, and a volcanic edifice that is not dead. The other is the behavior of lakes that can store dense gas at depth and release it with devastating consequences. The first is the Crater Lake problem. The second is the Lake Nyos problem. They share a volcanic setting, but not the same internal mechanics. NPS and USGS sources describe Crater Lake as a low-activity volcanic lake with a highly diluted chemical load, while Lake Nyos is documented by USGS as a stagnant, gas-rich lake that accumulated dissolved carbon dioxide until it suddenly discharged it in 1986. That comparison becomes clearer when the chemistry is put in context. Crater Lake's lake water is far from sterile, but the available USGS studies describe it as relatively dilute, well-mixed, and seasonally ventilated. Older USGS and NPS material notes that the lake's chemistry is not dominated by concentrated gas loading. Instead, it reflects a balance among precipitation, seepage, hydrothermal inputs, and atmospheric exchange. The hydrothermal contribution is real, but it is small relative to the lake volume, and its effects are spread through a very large body of water. That is why the lake can remain clear, blue, and biologically active while still carrying the signature of a restless volcanic system beneath it. Scientists have also learned that the lake is not static in its own right. USGS describes winter and early spring mixing that can reach the upper 200 to 250 meters, while deeper water exchanges with the rest of the lake on timescales of years rather than decades. More recent USGS modeling has looked at how warming air temperatures may alter that mixing pattern over time, because changes in circulation can affect oxygen content, clarity, and the transport of salts and heat through the water column. Those studies do not point to a looming gas catastrophe. They do, however, show that Crater Lake is sensitive to climate as well as volcanism, which means the lake can change without erupting at all. That matters because the public tends to collapse all volcanic lake hazards into one image, a hidden bubble of gas and a sudden suffocating cloud. In reality, volcanic lakes can pose very different threats. Some are acidic and hot. Some emit sulfur dioxide, hydrogen sulfide, carbon dioxide, or other gases at vents. Some are structurally unstable because magma or water may interact explosively. Some accumulate gas in the deep water column. Crater Lake falls into the lower activity category, where hydrothermal springs exist but are low in output, and where the lake's size and circulation suppress dangerous buildup. Lake Nyos, by contrast, is the opposite of that model, because its deep water remained chemically isolated enough for carbon dioxide to concentrate. There is a reason USGS continues to study Crater Lake as a volcanic system rather than merely a scenic lake. The agency says the lake sits atop Mount Mazama in the Cascade Range, where the Juan de Fuca plate subducts beneath North America, feeding magma systems that have produced the region's volcanoes. USGS also notes that volcanism continued inside the caldera after the Great Collapse, with later eruptions building Wizard Island and additional lava deposits. In other words, Crater Lake is not the final frozen memory of a vanished volcano. It is part of an active arc, and the water above it does not erase the heat below it. The most relevant fact for the gas question, however, is still the same one: the lake mixes. USGS explicitly states that the upper part of Crater Lake overturns and equilibrates with atmospheric gases twice a year, and that any excess dissolved carbon dioxide does not accumulate in lethal concentration. That single feature separates it sharply from the classic limnic eruption model. Even where hydrothermal fluids reach the bottom, they are dispersed through a large, deep, and seasonally ventilated basin. The lake may host unusual chemistry and underwater heat, but the structure of the water column works against the formation of a Nyos-style gas reservoir. That does not eliminate other hazards. USGS says the interaction between water and magma beneath Crater Lake could produce highly explosive hydrothermal eruptions that send rock fragments and large blocks out of the caldera. The agency also notes the presence of an active fault zone crossing the west half of the park, which could generate damaging earthquakes. Those are credible geological concerns because they arise directly from the volcano lake system itself. They are also different from a gas cloud scenario because they involve physical disruption of the lake floor or the volcanic structure, not the silent accumulation of carbon dioxide in deep water. This is why the lake remains the subject of periodic public anxiety whenever volcanic lakes are discussed. Crater Lake is among the few places where a visitor can stand on a rim, look into a basin of startling blue water, and know that the lake above the volcano is also the volcano's most effective disguise. The water hides the floor hides the vents hide the deeper system. Yet the scientific record to date keeps pointing in the same direction. There is hydrothermal activity, but no evidence of a Lake Nyos-style buildup of trapped gas. The hazard is real, but it's not the same hazard. Lake Nyos has become a symbol because the event was so devastating and so unusual. Crater Lake draws comparisons because it is also a volcanic lake with depth, stillness, and hidden heat. But the similarity ends where the chemistry begins. USGS documents for Nyos describe dangerous carbon dioxide accumulation in stagnant bottom waters, while Crater Lake's documents describe a lake that is regularly mixed, relatively dilute, and not prone to lethal gas storage. That is the central factual answer. The more interesting part is that Crater Lake still matters as a place where volcanic processes interact with water in ways that could change without much warning, even if gas accumulation is not the likely path. The hazards associated with Crater Lake do not announce themselves through the kind of quiet chemical buildup that defined Lake Nyos. They are mechanical, thermal, and structural, tied to the reality that the lake occupies a steep-walled volcanic caldera whose history includes collapse, eruption, and ongoing geothermal activity. The risks are less about invisible saturation and more about displacement, pressure, and sudden energy release within a confined basin of water nearly 600 meters, about 1,949 feet, deep. One of the most underappreciated threats in a caldera lake of this geometry is the potential for a large wave generated entirely within the basin. An inland tsunami does not require an ocean, it requires rapid displacement of water. At Crater Lake, the steep caldera walls rise sharply from the shoreline, and the submerged slopes continue down toward the deepest parts of the basin. If a significant landslide were to detach from the inner caldera wall and plunge into the lake, the volume of water displaced could generate a wave capable of traveling across the lake in minutes. The physics are straightforward. A mass of rock falling from even a few hundred meters above lake level into a confined basin can impart enormous kinetic energy. That energy transfers to the water column, forming a wave that propagates outward until it meets the opposite shore. Given the lake's diameter of roughly 8 to 10 kilometers, about 5 to 6 miles, a wave generated on one side could reach the far rim in a matter of minutes. The height of such a wave would depend on the volume and speed of the landslide, but even a moderate collapse could produce localized surges capable of overtopping low shoreline areas or impacting boats on the lake. Evidence of slope instability exists in the geological structure itself. The caldera was formed by collapse following the climactic eruption of Mount Mazama, leaving behind fractured rock, steep cliffs, and deposits that have been reworked over thousands of years. Weathering, freeze-thaw cycles, seismic shaking, and hydrothermal alteration all contribute to weakening these slopes. While there is no indication of an imminent large-scale collapse, the setting is inherently prone to episodic rockfall and, in rarer cases, larger mass movements. Seismic activity introduces another pathway to wave generation. The region lies within the Cascade volcanic arc, where tectonic and magmatic processes produce earthquakes of varying magnitudes. Even a moderate earthquake could destabilize sections of the caldera wall or disturb submerged sediment on the lake floor. A sudden slump of underwater material, even without a visible landslide from above, could displace water and initiate a basin-wide wave. This mechanism has been documented in other lakes and reservoirs worldwide, where subaqueous landslides generated unexpected surges. The interaction between volcanic processes and water introduces a different class of hazard. Crater Lake sits above an active magmatic system, and although no eruptions have occurred in recent history, the potential for future activity remains. The most likely form, according to existing geological assessments, would be a subaqueous eruption within the caldera. Such an event would not resemble a typical lava flow seen on land. Instead, it would involve magma rising through the lake floor and interacting directly with water. When magma encounters water under pressure, it can fragment violently in what is known as a phreatomagmatic eruption. The rapid conversion of water to steam can shatter magma into fine particles and eject both rock and water upward. In a confined basin like Crater Lake, this process could produce explosive bursts that send columns of water and debris into the air, generate shock waves across the lake surface, and trigger localized waves or surges. Even without a full magmatic eruption, hydrothermal explosions are a credible risk. These occur when water heated by underlying magma becomes pressurized beneath the surface and then suddenly flashes to steam. Unlike magmatic eruptions, hydrothermal explosions do not require fresh magma to reach the surface. They rely on existing heat and water trapped within the rock. At Crater Lake, where hydrothermal vents are already documented on the lake floor, a sudden pressure release could eject water, mud, and rock fragments with little warning. The consequences of such an explosion depend on its scale and location. A vent opening near the lake floor could produce a vertical jet of water and steam, disturbing the overlying water column and potentially generating waves. If the explosion occurred closer to the shoreline, it could directly impact nearby areas with debris and surging water. While these events are typically localized compared to large volcanic eruptions, their unpredictability makes them significant in a confined environment. Another hazard lies in the structural integrity of the caldera itself. The formation of Crater Lake was the result of a massive collapse following the evacuation of magma beneath Mount Mazama. The current basin is not a static structure, it is the remnant of a dynamic volcanic system. Faults cross parts of the caldera, particularly in the western region, indicating zones where the crust has fractured and could move again. Movement along these faults could trigger earthquakes, which in turn could destabilize slopes, disturb the lake floor, or alter the pathways of hydrothermal fluids. In that sense, the real hazard profile of Crater Lake is quieter than the Nyos scenario, but broader in scope. It is a system where water and volcano coexist, where depth and mixing prevent one kind of danger while leaving room for others. The lake does not conceal a single catastrophic mechanism waiting to be triggered. It contains a set of interacting processes that, under the right conditions, could produce rapid and localized disruption within an otherwise stable landscape.